All right, let's jump right into this. If you've ever looked at a major industrial facility, and I mean whether it's a massive chemical refinery, a power plant, or even just a large-scale food processing factory, you are going to see a total maze of pipes and these massive cylindrical tanks. Well, a huge number of those cylinders are actually shell and tube heat exchangers, and their job, it's basically to control extreme temperatures by transferring heat from one fluid to another without ever letting them actually mix. It is a massive industrial challenge, and getting it wrong can literally lead to catastrophic failures, or at best, millions of dollars in wasted energy. So, welcome to today's Explainer, where we're going to break down the exact step-by-step blueprint for engineering the perfect shell and tube heat exchanger.
Here's the roadmap for today's Explainer. We're going to start with the blueprint, hit the governing equations, dive into a real-world calculation, size the physical hardware, run those critical pressure drop safety checks, and then wrap up with our key takeaways.
All right, let's kick things off with phase one, the blueprint. So, how do engineers actually tackle a complex feat like this without just, resorting to guesswork? Well, they use a master recipe. We can take the 9 core design steps and neatly organize them into 5 essential phases. Now, you never start by just picking out metal tubes. You always start with the invisible energy requirements. First, we define the heat duty and the temperatures we're dealing with. Second, we calculate the temperature driving force and the overall heat transfer coefficient. It's only in step 3 that we figure out the total surface area required. Then, step 4, we size the actual physical tubes. And finally, step 5 is all about validation and safety. It's a remarkably logical flow, right? It takes us straight from abstract thermodynamics down to concrete steel.
Moving right along to phase 2, the governing equations.
To actually pull off this blueprint, we've got to unpack some heavy-hitting mathematical tools. A really crucial concept here is LMTD, or the log mean temperature difference. Now, before I just start throwing formulas at you, let's understand what this actually is conceptually. As a hot fluid and a cold fluid flow past each other through an exchanger, their temperatures are constantly changing, right? The temperature difference at the entrance isn't the same as the temperature difference at the exit. LMTD captures the true logarithmic average of this temperature difference across the entire length of the equipment. Think of it as the thermodynamic pressure, or really the driving force that's physically pushing the heat out of the hot fluid and into the cold fluid. Simply put, the higher the LMTD, the stronger the push.
And sitting right alongside LMTD is our core energy equation, heat duty, which is usually represented by the letter Q. This equation tells us exactly how much thermal energy needs to be moved. You simply take the mass flow rate of your fluid, multiply it by its specific heat, which, by the way, is just a measure of how much energy that specific substance can hold, and then multiply that by the temperature difference you want to achieve. It's pretty much the ultimate statement of energy balance.
Which brings us to phase 3, a real-world calculation.
Because, let's be honest, math is just theory until we actually apply it. So let's imagine a real crisis on the factory floor. We desperately need to cool down a massive flow of boiling hot ethanol. The raw data we're working with involves a hot process stream, an ethanol and water solution, coming in at a scalding 80 degrees Celsius. We need to drop that down to 40 degrees Celsius. And the volume here is absolutely huge. 10,000 kilograms of this ethanol solution are pumping through the pipes every single hour. To cool it, we're using standard utility cooling water, which comes in at 30 degrees and will be allowed to heat up to 40 degrees. Our mission? Figure out exactly how to build the equipment to make this specific cooling happen. So the very first step is figuring out the total energy load. When we plug our hot ethanol data into that heat duty equation we just looked at, and factoring in its specific heat of 3.6 kilojoules per kilogram degrees Celsius, the math reveals a massive energy load of 400 kilowatts. Just to give you a sense of scale here, a standard portable space heater you might plug into the wall at home uses about 1.5 kilowatts. We basically need to continuously remove the equivalent heat of over 260 of those space heaters running on full blast.
Next up, using our inlet and outlet temperatures, we calculate our log mean temperature difference. If we just crunch the raw math, we get 21.73 degrees Celsius. But here's the catch. In a real shell and tube exchanger, the fluids aren't flowing in a perfect straight line countercurrent setup. The shell fluid is constantly bouncing around these internal baffles. And because of this complex flow geometry, we have to apply a correction factor, which in this case is 0.90. That gives us our corrected LMTD of 19.56 degrees Celsius. And that is the true, realistic driving force we actually have to work with.
All right, phase 4, sizing the hardware.
Okay, we've got our energy load, and we have our driving force. Now we have to translate our 400 kilowatts of theoretical energy into physical metal. To find the physical size of our exchanger, we take our total heat duty of 400 kilowatts, and we divide it by our corrected LMTD and our overall heat transfer coefficient, or U value. For this specific ethanol-to-water system, engineering standards suggest assuming a U value of 800 watts per square meter Kelvin. When we crunch those numbers, it dictates that we need exactly 25.51 square meters of metal surface area facilitating the transfer of heat between these two fluids.
Now, obviously, we don't just build a giant flat sheet of metal. We use standardized 19.05 millimeter outer diameter stainless steel tubes. Each one is 4 meters long, arranged in a triangular pitch layout for maximum efficiency. If we divide our total required area by the surface area of one single tube, the math says we need exactly 107 tubes. But engineering reality is a lot different from textbook math. We almost never provide just the bare minimum. Instead, we install 110 tubes. And this brilliantly illustrates a key engineering principle. You absolutely must provide a safety margin for future fouling, because over time, scale and grime will build up inside these tubes, which reduces efficiency. Those 3 extra tubes, they ensure the factory keeps running even as the equipment gets dirty over the years.
But what about the cooling water? To safely absorb 400 kilowatts of heat, with the water itself exceeding its 40-degree limit, our system demands a really massive water flow. If we work the heat duty equation backward for the cold side, we find we need 9.57 kilograms of water per second. That translates to a whopping 34.5 cubic meters of cooling water pumping through those tubes every single hour.
Which takes us to phase 5, pressure drop safety checks.
So, we have a design that works perfectly on paper for transferring heat. But listen, no engineering design is ever complete without making absolutely sure it's not going to destroy our pumps or blow a gasket. When we run the validation on the shell side, where our ethanol is flowing, the allowable pressure drop limit is 25 kilopascals. Our calculated drop based on our geometry is only 18 kilopascals, so that's a pass. On the tube side, where our water flows, the limit is 50 kilopascals. We calculated 22 kilopascals. Another pass. This confirms our layout isn't just thermally efficient, it's mechanically safe, and it won't overburden the facility's pumping infrastructure. Finally, phase 6, key engineering takeaways. Let's wrap this up with a few universal golden rules that guarantee high performance in literally any design. First, everything comes back to the energy balance. The heat lost by the hot fluid must exactly equal the heat gained by the cold fluid. Second, your design is only as good as your geometry. Selecting the right overall heat transfer coefficient, tube size, and layout is absolutely critical, and you always pad the physical area for real-world fouling. Finally, remember that a heat exchanger isn't just a thermal device, it's a hydraulic one too. You must always verify the pressure drop to ensure safe, continuous operation.
As we finish out this explainer, I really want to leave you with this thought. We just walked through the industrial blueprint for cooling thousands of kilograms of harsh chemicals. But you know what? Thermodynamics doesn't care about scale. The very same LMTD calculations, energy balances, and pressure drop realities are quietly working right now inside your car's radiator, the coils behind your refrigerator, and the air conditioning unit keeping your home comfortable. The equations are entirely universal. So the next time you feel that blast of cool air on a hot day, you'll know exactly the invisible math that made it happen. Keep learning, and thanks so much for joining me.